Hello, my name is Zeeshan Asghar. I am presenting my project on 2D SLAM occupancy grid mapping with scan matching, FastSLAM and particle filters. This project focuses on autonomous mapping and localization using 2D LiDAR data. In this presentation, I will walk you through the problem we are addressing, the input and output data description, a high-level overview of our methodology, the main algorithms we have used, which include occupancy grid mapping, scan matching, and FastSLAM, a demo of the application, and lastly we will wrap up with conclusion and references. The core challenge of this project is to enable robots to simultaneously map an environment while accurately localizing themselves within it, commonly known as simultaneous localization and mapping. Our objective is to develop a 2D SLAM solution using FastSLAM with particle filters and scan matching. This setup allows us to generate accurate real-time maps even with noisy sensor data. Some of the key challenges we are tackling include handling sensor noise, correcting odometry drift, efficiently updating the map, and achieving loop closure for consistent updates. As shown in the image, even a small drift can result in a vastly different map if not taken care of. For this project, we have used two different datasets. One is captured in the Intel Research Lab and the other is from MIT Computer Science AI Lab. The Intel Research Lab dataset includes 2D LiDAR scan with 910 readings over a 180-degree field of view, along with X, Y, and theta odometry data. The MIT dataset provides similar LiDAR and odometry data but with 406 readings. The images shown are the ground truth for each dataset. After running the application, our final output includes occupancy grid map, a probabilistic map showing the environment, a robot trajectory that estimates path followed by the robot. The image of the final result of each dataset is shown. These appear quite similar to the ground truth shown in the previous slide. Additionally, output includes a GIF animation that shows the map updating over time and a TIFF file for the final map, georeferenced to real-world coordinates for each lab. The flowchart shows a high-level overview of the methodology we have used in our application. The occupancy grid mapping updates cells based on the LiDAR scan. The scan matching aligns new LiDAR data with the existing map to refine pose estimation, and the FastSLAM with particle filter provides probabilistic pose estimation by tracking multiple possible states. As represented in the image, in occupancy grid mapping, we divide the environment into a grid where each cell holds a probability of occupancy. The cells are updated based on the LiDAR data collected by the robot. This dynamic probabilistic map approach allows for continuous adjustment in the robot movement. The purpose of scan matching is to refine pose estimation by aligning LiDAR scans to existing map. An example of this is shown in the image. Our approach uses a multi-resolution strategy which makes the matching process efficient. This significantly reduces error and improves pose accuracy, leading to more reliable maps. FastSLAM is a core component of our approach. It uses particles to represent possible robot poses, which are then weighted based on their match with the sensor data. The key elements include particle filter. They help manage different possible positions of the robot. Important sampling retains the most probable particles for refined poses, and loop closure corrects the map when the robot revisits previously mapped area. The image shows the partially observable Markov decision process representation of SLAM, which we have used in our application. Now let's look at the demo of the SLAM system in action. The one on the left is for Intel dataset and the one on the right is for the MIT dataset. We are doing real-time mapping. The map is being built as LiDAR data is processed. You can see the estimated path followed by the robot. We can also observe loop closure in action as the system corrects the map when the robot revisits areas. In conclusion, this project successfully implemented a 2D SLAM solution that enables robots to map their environment and localize simultaneously. The combining occupancy, grid mapping, scan matching, and FastSLAM algorithm with particle filters, we built a system capable of handling real-world challenges like sensor noise, odometry drift, and efficient map updates. Our approach was informed by key resources that provided both fundamental theories and practical insight. The Intel Research Lab and MIT Computer Science and AI Lab dataset provided critical LiDAR and odometry data for testing as well as ground truth data for verifying our results. Research papers such as FastSLAM effective solution to simultaneous localization mapping problem guided our understanding of particle filters in SLAM, while the frame-to-frame scan matching for 2D LiDARs offered a refined approach to scan matching. The Coursera's motion planning for self-driving car course also helped us solidify concepts related to occupancy grid essential for dynamic map updating.